Recharging and scheduling nodes in a Wi-Fi network. Presentation outline. First, I would like to introduce some background information of the thesis and then project aim as well as the problem being addressed. Briefly mention the literature reviews, simulation results, and the plan for Active 458. Background information. Wireless power transfer is a technology that enables power transmission through air gap instead of cables. Wireless power transfer has already been implemented in many applications such as electric toothbrush, drones, portable devices, and electric cars. The technology behind these applications can be categorized into two types. First, near-field wireless power transfer, also known as non-radiative wireless power transfer. It uses either electric or magnetic field to transmit energy within a short range. The two most commonly used methods are inductive coupling and magnetic resonant coupling. This graph shows the basic idea of inductive coupling. It consists of two coils, one for transmitting and one for receiving. The transmitting coil is connected to an AC power source and it generates an alternating magnetic field. According to Faraday's laws of induction, this alternating magnetic field induces alternating current in receiving coils so that the load on the circuit can be powered. Resonant coupling uses the similar ideas of inductive coupling. The only difference is it contains two more circuits. These two circuits resonate at the same frequency and it increases the power transmission range and transmission frequency. The charging distance of near-field wireless power transfer can reach up to 2 meters. The power transmission efficiency is generally around 80 to 90%. The second category is far-field wireless power transfer. It uses radio frequency to transmit power through a long distance. Radio frequency is defined to be any of the electromagnetic waves frequency that ranges from 3 kHz to 300 GHz. A good example of RF power transfer is microwave. Actually, in our daily life, RF is emitted from multiple sources such as TVs, radios, and Wi-Fi networks, mobile phones, and satellite communications. RF energy harvesting technology takes advantage of ambient RFs, and it converts RF energy into electricity. The charging distance of far-field wireless power transfer can reach up to 4 kilometers. RF energy harvesting technology is also categorized into two types: ambient RF harvesting and a dedicated ambient and a dedicated RF harvesting. Ambient RF harvesting harvests RF from ambient RF sources such as TVs and Wi-Fi networks. It powers low-power devices. The current product includes stick-in charger and 3-volt harvester. This picture shows stick-in charger. This little plug on the right-hand corner is stick-in charger. Once it's been plugged into a mobile phone, the mobile phone will start charging just by harvesting the ambient RFs. The other product is 3-volt harvester. This harvester has the same size of your ID card. It provides enough power for low power devices such as a security camera and smoke detectors. It harvests RF and converts it to electricity constantly. dedicated RF harvesting harvests RF from a dedicated source. Quota wireless charger uses this technology. This Wi-Fi charger emits a 2.4 GHz radio frequency to power mobile phone within a range 30 feet radius. Once the mobile phone sender request to the wireless charger, it'll start charging the mobile immediately within an effective range. The incoming iPhone 7 is using the similar technology for wireless charging capability. This thesis mainly focuses on RF energy harvesting. It aims to apply RF harvesting technology in Wi-Fi networks to power mobile devices and investigates the probability and the feasibility of using access point to recharge mobile devices. This would enable a real hands-free charging capability and let mobile devices never die because of batteries under a Wi-Fi environment. The designed wireless network architecture consists of a central controller, a number of access points that are responsible for data transmission and the devices recharging, as well as a number of users that rely on access points for energy. The problem of interest to this thesis is how to schedule packets to the surrounding devices such that the network capacity is maximized while at the same time meet the energy requirements of RF harvesting nodes. The literature that has been reviewed about RF harvesting on wireless networks can be divided into three types according to the network types: small cell networks, wireless sensor networks, and wireless local area networks. Small cell networks is the key feature of fifth generation networks. RF harvesting is applied to power base stations so that it reduces power consumption even when the network is densely deployed. RF harvesting on wireless sensor networks releases sensors from the limitation of batteries and extend the lifetime of sensor networks. The purpose of RF harvesting in Wi-Fi networks is to power mobile devices. However, the biggest challenge is the interference between power transmission and data transmission. The simulation results. The simulated network consists of 6 access points and 3 energy harvested nodes. It investigates the relationship between packet arrival rate and harvested energy level of each of the energy harvested nodes. As it can be seen from the graph, packet arrival rate is positively proportional to the amount of harvested energy. Higher packet arrival rate means more packet transmission. It provides more RFs for the harvester. However, the energy harvested node 1 didn't increase dramatically as the other two nodes. This is because the distance between energy harvested node 1 and the 5 access points are too long. Energy harvesting node 1 is too far away from all of the access points. According to Free's transmission equation, distance between energy harvesting nodes and access points affect the amount of harvested energy dramatically, exponentially. Therefore, Even packet arrival rate increases from 0 to 100. The harvested energy by node 1 only slightly increased. The plan for Active 458. The further simulation is necessary to investigate more factors that affect harvested energy level. Because current simulation only considers all the packet size are the same, and the data transmission rate is a constant. However, in practice, packet size is varies and packet transmission rate changes according to different situations. Also, in Active 458, a packet scheduling method that meets the energy requirements of RF harvesting nodes and at the meantime maximize network capacity need to be developed.